Here, we will discuss total stresses, effective stresses and pore water pressures. At a point within water, the pressure P is hydrostatic and is equal all around in all directions. It is given by the depth Z times the unit weight of water. In soils, the vertical overburden stress is given by the depth Z times the unit weight of the soil. Unlike water, the horizontal stress is not the same as the vertical stress in soils, in fact it is often much less. We will use the subscripts V and H to denote vertical and horizontal stresses. We will discuss only the vertical stresses for now. When there are few layers of different soils present above a point A, we include all of them in computing the vertical overburden stress. If there is surcharge Q at the ground level, that has to be added to the vertical overburden stress. Let's consider a point A within a soil that is submerged. The vertical normal stress at this point is shared by the water and the soil grains. The fraction carried by the soil grains or soil skeleton is called the effective stress sigma prime, and the fraction carried by the water is known as the pore water pressure U. We use a prime to denote the effective stress and no prime for the total stress. While the pore water pressure is the same in all directions, the total and effective stresses vary with directions. At all points within the soil and at all times, total stress equals effective stress plus pore water pressure. This is known as Terzaghi's effective stress principle. Terzaghi's effective stress principle is applicable in any direction. Here, we have applied this vertically and horizontally. To estimate the overburden stresses, we often assume unit weights for the different soils. Here, we have some typical values of bulk and saturated unit weights. As you can expect, dense granular soils are slightly heavier than the loose ones, and they are little more heavier when saturated compared to bulk. In the case of clays, the bulk and saturated unit weights are the same due to capillary If we place a capillary tube in water, there is an immediate rise of water within the tube which is called the capillary rise Hc. The capillary water column is held by the surface tension T right around the inner tube, acting at an angle alpha to the vertical. By equilibrium considerations, we see that Hc in meters is equal to 0.03 on d, where d is in millimeters. Smaller the tube diameter d, larger the capillary rise h. C. The interconnected voids act as pore channels that can draw water into the capillary zone. The pore channel diameter can be estimated as 1/5 of d10. In the capillary zone, the pore water pressures are negative. The water is under suction.